All right, greetings everyone. You have made it to the sixth and final video of section 8.4. I know it seems like there's a lot in this section, and there is, so I'm actually not going to apologize for that. Also, your physics instructors that you're going to have will be very angry with me if I don't thoroughly teach you about vectors, so that's why we're going through all of this. All right, so look at some final examples here. So we're going to look at plane flights and how their velocities and directions can be impacted by the wind. So let's say that we have a plane that's traveling directly north with a speed of 400 miles per hour with respect to the ground. And we want to determine the resultant velocity of the plane. So we're looking for only the magnitude of a vector here if it encounters each of the following: either a 10-mile-an-hour headwind or a 10-mile-an-hour tailwind. Now, to think about this, what we're going to do is, I'm sure you could probably figure out these numbers kind of in your head, but we want to use vectors to model what's going on here. So we're going to start with the headwind. So thinking about, we have a plane going directly north at a velocity of 400 miles per hour. If I call this vector, I'm going to call it P to represent the path of the plane. Then in this case, we know that the magnitude of P is 400 miles per hour. And then we want to draw a vector that represents the headwind. Now, a headwind, if you think about it, I mean, I say that word head, so it must mean it impacts your head some ways, is a wind that would be going the opposite direction of you, right? So it would be a wind, or it could be represented by a vector like this, going in the exact opposite direction. So it'd be going southerly from the direction that the plane is going. And if I call that vector, let's say W, then the magnitude of W would be 10 miles per hour. And we want to figure out what happens to the velocity of the plane when it encounters this headwind. And so vector-wise, what we can do is actually take and add these two vectors together, which means we take the initial point of W and put it at the terminal point of P. So it looks something like this. So there's that vector W there. And then the resultant vector, remember, will go from the initial point of P to the terminal point of W. So this would be a resultant vector here. And we'll call that vector V. And what will the magnitude of V be? Well, again, the original vector had a magnitude of 400 miles per hour. We've got a magnitude of 10 miles per hour going acting in the exact opposite direction. So as you might imagine, the resultant vector is going to have a magnitude of 390 miles per hour. Okay, so that's what that would look like. All right, let's look at the second example then. So here now we've got the same plane still flying 400 miles per hour directly north. But now it's encountering a tailwind of 10 miles an hour. And what does that mean? Well, tailwind, again, if you think about that word tail, it means like wind that's going to come from your tail, and it would actually be one that's going to help you along, right? So that's actually going to be a wind, a vector that I'll call it Z in this case. That's going in the same direction of the plane. And in this case, it again has a magnitude of 10 miles an hour. And again, if we add it, take its initial point, put it at the terminal point of P, add those two together, the resultant vector that we get, starting at the initial point of P, now going all the way up to the terminal point of Z, that would give us a vector I'll call it Q. And the magnitude of Q in this point, well, again, the tailwind is helping in this case, so it's actually going to make the plane go faster. So it's going to give us a magnitude of 410 miles per hour in this case. Okay. And again, I know you probably could have figured those out maybe without using vectors, but since that's what we're doing in this section, we want to think about them that way. All right, so let's look at one more example with this then. So we have the same plane still traveling at 400 miles per hour due north, but this time we're told that there's a crosswind blowing from the northwest at 10 miles an hour. So this is going to be something a little bit different. So we again have this 400 mile an hour vector P, so where the magnitude is 400 miles per hour. And we have a crosswind wind blowing from the northwest, right? So let's first of all think about what that means. So if I draw my little compass over here, here's the north, east, south, and west. If the wind is coming from the northwest, and that means it's coming from this direction, which means it's actually going to be blowing southeast, right? So it's coming from the northwest, it's blowing southeast, and we'll assume it's going directly southeast, which means that its angles on each side here, it's going to split that up into two 45-degree angles. Okay, and I'm going to, because I'm running out of creativity, I'm just going to call this vector W again. And the magnitude there is still 10 miles an hour. And so to see how it impacts the velocity of the plane, what we'll do is we'll take and actually add this again to the end of the vector P. So in this case, we'll get something that looks like this. Okay, so this will be our vector W. And then we draw a resultant vector this time. So going from the initial point of P to the terminal point of W. Notice that in this case, not only has our magnitude changed, our velocity, but also our direction of the plane has been altered by that wind. Okay, and so that's what we're going to figure out here is the new magnitude or speed and the new direction. Now, what is the thing I wanted to do? Oh, I'm going to call this vector here representing the new direction and magnitude of the plane. I'm going to call that C. So we need to find the resultant speed. We need to find the magnitude of C. And we also know that the magnitude of W is 10 miles an hour. And that this angle in here is a 45-degree angle. And we could break these vectors down into their components again, add them up, you find the magnitude of the resultant vector to help us find the magnitude of C. But in this case, what's really nice that happens, you probably see, is that we end up with a triangle here with these vectors. And if we think of their magnitudes as being the lengths of the sides, we'll notice we have a side here. Whoa, not like that though. We have a side here, an angle here, and a side here. We're trying to find the length of the opposite side over here, which tells us we can use our good friend, the law of cosines, then to find that magnitude. So we can do, for simplicity's sake, I'm just going to say C squared equals the length of the first side, 400 squared, plus the length of the second side, which is 10 squared, minus 2 times 400 times 10 times cosine of the angle in between, which is the 45-degree angle. If you work that out, we end up with C squared equals 154,443.1458. You can take the square root on both sides to solve for C. And when we do that and plug it into our calculators, looks like we end up with C equals 392.993 miles per hour. Okay, so the resultant vector there, the resultant velocity, I should say, ends up being 392.993 miles per hour. All right. Cool. Let me erase a few things here. As I said, I didn't use quite correct notation here, so I'm going to use it this time now. So again, we just found the magnitude of C is 392.993 miles per hour. Let's look at the next question. Next question asks us, now that we have that, how many degrees off course will the plane end up flying, right? So again, it was going directly north, then it got hit by this crosswind, and now it's kind of going in this northeasterly direction. And we want to know how much has it been blown off course, which means we really want to find the measure of this angle in here. And we could use components of vectors and whatnot to solve this. But what I'm going to do instead is use the properties of this triangle. And I know I have the length of this side here and the length of its opposite angle. I have the length of this side here, and I'm trying to find the length of its opposite angle, which tells me I can use the law of sines. So I could do sine of 45 degrees over 392.993 equals the sine, and I'll call it theta, the angle we're looking for, over length of the side we know, which is 10. Can isolate sine of theta to get sine of theta equals 10 times sine 45 degrees over 392.993. And then to find theta, we'll do inverse or arc sine of 10 times sine of 45 degrees over 392.993. Sorry, I'm running out of room down here. When I plug that into my calculator, I find that the measure of the angle there is 1.0310 degrees. So it looks like it's being blown off course about that much. Okay. Now, one thing we need to check here, remember when you use law of sines to find an angle, sometimes there's a separate or another angle we can find. So remember, we did inverse sine of that, and we got 1.013 degrees, which would be in the first quadrant. We might also have an angle in the second quadrant. We do 180 minus that. But in this case, when we do that, we get 178.969 degrees, which, notice because there's also a 45-degree angle already in the triangle, then we can't have 175 as well, because, or 178, excuse me, because if we added those two, we'd be over 180 degrees. So it tells us the only answer here is 1.0310 degrees. Okay. All right, that's it for now. Thank you for watching.